you guys have a test on Thursday. I was talking about my Physics 21 class at the University of Missouri. It's one of the hardest classes that I ever took. And I would probably start studying an average of I'd put in 16 hours easily before every test. I would start studying at least 4 days in advance for my Physics 21 exam. And that was even going to class and working all those problems and going to get help at the physics tutorial sessions that were on Tuesday nights all the way across the campus. So I'm just telling you, like, this can be a difficult test, and you guys have to put in the hours to study. I'll never forget when that first test came back in my Physics 21 class. You know what I got on it? 64%. 64 out of 100, right? I was like, crud. First test, I already have a D in this class. Like, this is going to be awful, right? One of the highest grades in the class. The average was 23. 23. So I got a 64% after like 14 hours of studying, but I guess it paid off. But man, that was a hard class. But sometimes you got to put in the effort. I'd march myself across campus on a cold night every Tuesday to go to tutoring to make sure that I could pass that class. So remember that I'm here in the afternoons, guys, and I am willing to tutor. One of the best things that you guys can do is go back and look at these worksheets like these. I don't answer all those questions. Go back and look at the questions I did answer. Make sure you understand them, because you're going to see questions like this on your exam. The ones that you don't know how to answer, circle them and then get on that meet with me in the afternoon, and I will go through those and make sure that you guys understand those, okay? So I am here to help, but I cannot help you unless you show up and you tell me what you need help with, okay? All right, you guys are going to stay there, but I'm going to go ahead and open up just Google Classroom because I wanted to show you. This was from last class, okay? So you're going to recognize this. Hopefully this idea, that image is kind of in your brains, and just remember what you guys had to do, right? You had to take the initial mass, you had to get your final mass, and you had to calculate percent change in mass, and you guys had to graph, okay? Now, I had you do this to warm you up to the potato water potential lab, which I knew we were going to be talking about in lecture 6. One thing I want to show you guys, because I had some people that told me that their graph disappeared. Guys, if you click X, it doesn't disappear. All you have to do is open up the extension and it comes back. The only way to get this stuff to disappear, by the way, is if you hit the recycle button. So just FYI, if you choose to use this and you think it's easy to graph with it, then if you accidentally hit the exit button, don't freak out that you did all that work for nothing. Just click the extension and it all comes back, okay? All right, the reason why I wanted to start with this, though, is because, get rid of that, is because I had a lot of people not know what to put on the graph. On the AP exam, you probably will have to graph. And the instructions aren't going to be graph the data. They're going to tell you something like what I have highlighted here. Design a graph that shows percent change in mass. That's one thing. Over tonicity. Over, by the way. So it means tonicity is on the bottom. That means it goes on the x-axis. They gave you the two things. The tonicity or the concentration will be the IV. The percent change in mass should be the DV. So now you know you got two things for your two axis right there. They will tell you what to put on your axis, okay, and what to graph. And by the way, just to make sure you understand, in a table, your IV stuff usually comes first. And it can either be like this first column or it might be along the first row, okay? But wherever it's at, your DV comes next. So if your IV is here, then your DV is going to be on this side of the graph. If your IV is listed across a row, then that means that what falls below that is your DV, okay? So in this case, my IV is I'm changing the sugar concentrations. You guys had to mix those up. And then I am calculating, I'm getting data, and that was my percent change in mass. So those numbers that you calculate or you get at the end is going to be representing your dependent variable, and your dependent variable always goes on that y-axis, okay? So keep that in mind because you're going to make that graph very similar to that today, okay? All right, so let's get into, and I'm going to start with what you guys already know. We're going to flip to page 3, okay? Now, without teaching you anything about water potential, take a look at A. Note that this is a U-tube, and in a U-tube, when you set this up, you have a membrane that you put here, and so molecules can cross that membrane. Now, when we're dealing with a U-tube like this one, we show you solutes. The solutes usually can't cross that membrane, but water can, Okay. So A, just applying with what you guys learned last class, I want you to put an arrow to show me which way water is going to move. Is it going to move from the left to the right or the right to the left? Go ahead and put an arrow there. Okay, so if you just apply the rule that solutes suck, you should be able to tell me that water is going to move in that direction. Okay, now let's relate that to something new, water potential. So water potential, you need to memorize that water always moves, and this is our symbol for water potential. Water potential, or water always moves from an area of high water potential down to an area of low water potential. It's just like water moves from high concentrations to low concentrations. I'm not changing really much there, just adding water potential there, okay? So now let's relate that to what they give you. They actually give you water potential. So they calculated the water potential of this solution over here, and they calculated the water potential of that solution over there. Negative 0.23 is lower than 0. So water is moving from an area of high water potential over here, where there's an area of low water potential, okay? So what is water potential? It's the potential of water to move, and we factor in two things. You guys already know that solute affects the movement of water, but guess what else can affect the movement of water? And it's this value right here. That P stands for pressure. So water potential factors in pressure and the solutes of a solution, which kind of brings me to, let's talk about this pressure part real quick. And I lost a syringe. Oh, here it is. That's going to be sticky. Oh, well. Okay. So here we go. I have a syringe and it's filled with water. Okay. Is the water coming out of my syringe? No. So the potential of the water to leave is 0. Does it make sense? The potential for the water to leave is 0. It's not leaving. It has no potential to move. It's staying in my syringe, right? Now, we all know how I can get water to come out of the syringe, right? I increase the pressure. Then is my water going to move? Yes. So if I up the pressure, my water has potential to move, to leave that system, okay? That's what this is showing you. It's the same setup, okay? It's the same setup. But look what they're doing. They're putting, this is like kind of like a syringe stopper here. They're pushing down. They are upping the pressure. Well, do you see the difference now? My pressure was 0, but now my pressure value went up because they're adding pressure to the system, okay? Now, note what happens now to my water potential. If pressure goes up, what happened to my water potential value? You see it? It was at negative 23, and now it's at 0. That's a direct relationship. So if you increase the pressure on a system, you're going to cause the water to have a higher potential to move. So you need to be able to tell me that if you increase pressure, water potential also increases. Okay, and that's what it did. It increased. It went from negative 0.23 up to a 0. Which way is water going to move? Both directions. Let's look. You see how your water potentials are equal? So if some water moves over here, then some water is going to move over there. Interesting, because even though there's solutes, those solutes the water can't cross into those solutes. Why? Because you up the pressure. And it's imagine if you had a tire with high pressure and you open the valve and you try to put more air in your tire that has high pressure. Isn't the air coming out? Like, you can't do that, right? So let's take a look, and then let's add even more pressure. So see how they put a bigger arrow here? They push that plunger further down, okay? Notice my pressure value now. It went up, okay? My solutes are the same. I haven't added any solutes. There's still a bunch in there, right? So my solute value hasn't changed, but let's take a look at my water potential value. Now it's positive 0.07. Compared to this side, it's still 0. By the way, open beaker, pure water potential is always 0. So this solution over here, that's something you need to have memorized, but it's also on your formula sheet for you. Okay, so if I ask you, what is the direction water is going to move? What would you put? What is the direction that water is going to move?
Into the the left one because it doesn't have any, because its water pressure is less.
Thank you. Awesome. So here's a situation. We reversed osmosis. Have you guys ever heard of reverse osmosis? Yes, you have. I have students ask me this all the time. Miss Spencer, what's reverse osmosis? Do you know where we see that term, reverse osmosis? Anyone have a water bottle? Look at the water bottle on the back. It says purified by reverse osmosis. So osmosis is the flow of water, right? From high concentrations to low concentrations. That's not happening there. It's actually flowing from low concentrations of water to high concentrations of water because we up the pressure. That's reverse osmosis. So this is how we purify water before we bottle it. By the way, if you have bottled water and it doesn't say purified by reverse osmosis, do you know where that water is coming from? Let's say that bottling company is in Detroit. Okay, that water is out of the tap in someone's just tap water in Detroit. Did you know that? Is anybody else can market bottled water? Like in Kansas City, I can open up the tap at my house and I can fill up water and I can seal it and I can sell you water. I didn't put that it's purified, right? So just FYI, if it's not purified, then they won't say like purified by reverse osmosis. And by the way, Kansas City has like the second highest, like best water quality drinking water in the nation. New York is first though. Okay. So anyway, if you then like get bottled water from like Seattle and it's not actually purified water, you're probably drinking like tap water from Seattle and it's at a lower water quality than if you just turned on your tap here in Kansas City. So that's reverse osmosis. So notice that in this situation, we have high water potential now because we up the pressure. And on this side, now we created where there's low water potential. So that's why the water moves in that direction. Okay. All right. So flat out have memorized open beaker, no solutes. Okay. So an open beaker, that means I'm not putting any pressure or anything like that on the surface of this water. So if it's an open beaker, your pressure on that water is zero. It's even. We're not getting water flowing up or down because we're not like adding pressure or making negative pressure. Solute potential, no solute. So my solute potential is zero. And now let's get to that equation. Water potential is just you got to add together the solute potential and the pressure potential. So that's easy. 0 plus 0. So the water potential of this beaker is 0. Okay. By the way, in the formula sheets here, I already wrote all over it. Let me erase this real quick. Oh, no, my paper towel is wet, so it doesn't want to take off my non-polar dry erase molecule. Okay. So now I'm on this part of your formula sheet. So this whole section right here is about this last lecture, right? And knowing how to use this information. They tell you right there, open container is 0. Just FYI, if you have an open container, the pressure potential is 0. So if there's no solutes, then my water potential is 0. All right. Now, let's go back. We already talked about if pressure goes up, what happens to water potential? Water potential goes up. If I add pressure, that water is going to leave. It has a great potential to leave. Okay. The opposite happens if I add solutes. So I'm adding solutes now. Okay, remember my pressure potential was 0. So is it going to now be a positive number or is it going to be a negative number? Okay, you need to know that if you add solutes, so if I add solutes, it's an inverse relationship. The potential of water to leave that area is going to decline. It's going to go down. Water potential is going to decrease. Okay, so if I add solutes and it started out with a water potential of 0, now the water potential is going to be something that's in a negative, like negative 0.2 bars or something like that. So if you add solutes, the water doesn't want to leave that solution, right? Because we know solutes suck, right? All right, let's talk about some easy problems. Let's do this one right here because it's got a negative. Sometimes negatives throw you guys off, okay? If I said there's 2 solutions, this is a membrane, water can cross. Which way is water going to move? It's pretty simple. High water potential to low water potential. Sometimes at 0, everyone thinks 0 is bad, right? But hey, if you have a 0 bank account, it's a lot better than a negative 2.3, right? Negative 2.3 is lower. Water always moves from high water potential to low water potential. Let's show you now a problem in relation to cells. So let's go to number 10. I just flipped it to that last page, third page. Okay. Can anyone tell me the gap junctions so that molecules from the cytoplasm of one plant cell can actually flow into the cytoplasm of other cells? Do you remember what those are called? Plant gap junctions. It does kind of start with plant, PLA, called not plasmodesmata. You guys ever heard of stomata? Stomata? Okay, well, you will. Stomata is the holes in the leaves where the gas is exchanged. We're actually going to look at them maybe under a microscope if I ever see you guys again. So desmata, I think, means like a hole or something. So we have these gap junctions. All right, which way is the water going to move? Is it going to go from A to B, B to A to C, C to B? High water potential to low water potential. So in this case, water would flow from A to C. Water would then go from C to B. Water would also go from A to B because the water potential is the lowest in cell B. These are all higher. Okay. All right. So simple, high water potential, low water potential. All right. Let's do some math. Yay. There are two equations. Expect to see these suckers on the test. So I already showed you the first one, right? Okay. Let's apply it. This is the easiest types of questions that you're going to see about water potential. If I need to calculate the water potential of the beaker, so notice I've got a beaker and I have a dialysis bag. Okay, so this makes sense. I have dialysis bag in a beaker solution. This is back on page 1. And let's see what they give me about the beaker. So I'm reading and I'm like, oh, okay, well, they give me solute potential there. That has a little S on it, right? Well, if you know water potential, all we need is solute potential plus pressure. Okay. This is an open beaker, so what's my pressure? 0. They give me solute potential. This is like some 5th grade math right here, right? We got this. So the water potential of the beaker is -4. By the way, the units are bars. If you ever want me to show you how the units cancel out so you're left with bars, I'll be happy to do that, but it's bars. So in the beaker, I'm just going to put my water potential equals -4 for reference. Okay. All right. Calculate the initial water potential of the bag. So let's go down here to the bag. Let's see what they gave me. Oh, sweet. They gave me both of them. So I have water potential equals solute potential plus pressure potential. Plug and chug. So water potential equals -1 plus 0. So water potential equals -1 bars. That was the bag. So I'm going to put -1 in there for reference. Apply the rule. Now, before I even taught you about water potential, if I asked you guys to predict which way water is going to move, couldn't you do that? Without even water potential. Do you see that they got sugar solutions? That we have a sugar solution in the beaker. We have a sugar solution in the bag. Where is there more sugar? There's more sugar in the beaker. Solutes suck. Water should move out. If you just even apply solutes suck, you guys would be able to figure out water moved out, right? That's from last class. But now let's just link it to water potential. Water's moving from high water potential. -1 is a higher value than -4. So the water is moving from high water potential to an area of lower water potential. That's what C was. It's the way that water always moves, okay? Now, the next part is, this one's the trickier problem. I would say this is the trickiest out of all the water potential problems. Okay, does it make sense that water is going to move until equilibrium is reached? What do we mean by equilibrium? And what that means is, I'm going to go ahead and I'm going to draw that dialysis bag again. Okay, just for reference here, because that one's getting a little bogged up here. Until water potential in and water potential in the bag and in this are equal. That's what we mean by equilibrium. When the water potential values become equal in these two solutions, then we don't have a net flow of water into the bag or out of the bag. Some water will go in, some water will come out, okay? So this is the tricky part, is understanding that water is going to move across this membrane. But for most membranes, the solutes can't cross. Like there's plenty of cells like can't take solutes in or out because they don't make a transport protein for those things to move. But water can just go through aquaporins from high concentrations, low concentrations, okay? So here's what's going to happen is let's think about what's going to happen here, okay? My solutes aren't going to change. The solutes aren't going to cross, okay? So, but water is, okay? So my solute values aren't going to change, okay? Solutes are going to stay the same. But what is going to change is pressure. You're going to show me something with your cameras on and your hands in the air, okay? You're either going to show me up or you're going to show me down. Let's think about this. We know that water is going to leave, right? What is going to happen to the pressure of that bag? Is the pressure going to go up if water's leaving, or is it going to go down? And if you don't know what's happening to pressure in this situation, most of you drive, think about a tire. And what's happening to pressure if air is leaving your tire, okay? So show me. Is pressure going to go up or go down? Thank you, okay? So the pressure changes, but our solute value doesn't, okay? So we're going to see some change happen here until the water potential inside equals the outside. So the inside water potential is going to equal the outside water potential, okay? So what is my outside water potential? Because the pressure of it's not going to change and the solutes aren't going to change. It's right here. It's -4. We calculated it. Okay? So here's what's going to happen. Here's our inside. We know that inside we have solute and we have pressure. And eventually, those are going to add together to equal the outside water potential, -4 bars. Okay? What's my solute? My solute isn't going to change. So in the bag, my solute potential is -1. Pressure, I'm going to just kind of indicate here. Pressure is what's going to change because water is leaving that bag. Okay? So that's what we're trying to solve. Trying to get that new pressure, because that's what the question says. What will be the new pressure potential of the dialysis bag once it has reached equilibrium? And that means once it has reached what the outside solution is, which is -4. Okay, so what's this value going to be? What's going to be my new pressure?
-3.
Thank you. There's my answer.
Also, I got a question.
Sure.
Wouldn't, if you add more water to the outside, won't that like dilute the beaker and decrease the like water potential of the beaker from the dilution of the water?
Technically, yes. So if water is leaving, it would. But I wonder if because water is leaving, so if water is leaving to the outside solution, if you put more water in that beaker, would it also affect the pressure? So would that pressure value then alter as well to keep it at that -4? That would be my guess in that situation. Okay. All right. So our pressure was adjusted until we got the water potential inside equaling that water potential outside. Okay. All right. Let's move on to our next equation that is in that box. Okay. And notice We've seen that symbol before. We saw it right here. Sometimes they have you use this equation to calculate the solute potential, and then you just take that number and you put it in for solute potential, okay? So this equation is negative ICRT. Look, it's all defined for you. It says when we talk about sugar solutions, which, by the way, these potatoes are sitting in sugar solutions here, okay? We are always going to use an ionization constant of 1. The molar concentration, this is so critical that you guys understand some of these very simple ideas. Does anyone know what the symbol for moles is, or molar concentration? Guess. What do you think the symbol is?
Isn't it a big M?
Thank you. So when you're trying to figure out a number for C, go find a number that has a big fat M after it. Then you found it. You found what C is. Use the units. The units will be your guide, okay? So if you need to find a number for molar concentration, it better be like 0.4 M, have an M behind it, okay? The R, you're always going to use that value, and the temperature. If they give you degrees Celsius, you have to turn it into Kelvin, but they're going to tell you just add 273 to it, okay? All right, so that's what this type of problem looks like. So it wants to know the solute potential, and they start giving you M, they start giving you a temperature. So you're like, okay, I need to use this equation. Solute potential equals negative ICRT. Plug and chug. So to calculate solute potential, my ionization constant, notice that it has it like in a sugar type solution. Sugar doesn't break into ions. So that's why it's telling you that the ionization constant, or like sucrose and glucose, is always going to be a 1, okay? If it was sodium chloride, NaCl, that breaks into 2 ions. So the ionization constant would be 2, by the way, but I don't think you'll ever know that. C, they gave it to you. There's C. It's got M behind it. So 0.5 M, R, 0.0851. And for the temperature, I have to take 20 plus 273, and that equals 293K. 293K is the temperature that I put in there, okay? So when you do that, solute potential equals, it's like -2, and I'm just guessing off the top of my head. And by the way, all of these units that I didn't write out here, they all cancel except there's one left over, which is bars. And that's how we then, that's our units for solute potential and water potential and pressure potential. Pressure can be in bars, okay? All right, so if we know a solute potential, we can calculate the water potential. So if I know solute potential, and by the way, if they don't give you pressure potential, always assume that it's 0, that it's an open system. Okay, so pressure potential is 0, and I calculated my solute potential here, which is -12.1, then that is my water potential. So water potential equals -12.1 bars would be my answer. Okay. All right. Let's take a look at this graph. Does that jog your memory? Because now we're going to do the water potential lab, and this is what it looks like. Okay, so imagine if I handed you guys a strawberry in class. I put it on your lab table, and I said, okay, guys, figure out what the water potential of a strawberry cell is. You could do this in class. And this is how you would do it. You would set up different sugar solutions. I just have them dyed to kind of keep track of which is which, right? So I know that these are actually, those are potato cores. So I just basically made like French fries with my little potato core here. And so these potato cells are sitting in distilled water. I want to show you, like, this thing is solid, okay? You can hear it because it's full of water, because this was distilled water and all the water is going into the solutes, like where the starch is at, which is in those potato cells, okay? So the cells have really high turgor pressure. And so when cells are full, plants are upright because their cells are really tight, okay? Out of all of these solutions, this is the highest sugar solution. It's a 0.1 M. I got a lot of sugar in there. Let me show you these potato cells. They've been sitting in there since 8 a.m. this morning. Okay, here it is. All right. So you can see that these cells have really low pressure, low trigger pressure. It's the coolest feeling though. Some of you guys have felt these before in my pre-AP class. And this is what happens whenever you pull water out of plant cells, or plant cells don't have a lot of water. They just fall over, they're wilted, okay? So obviously water left these cells because the sugar water pulled, solute suck pulled the water out of those potato cells, okay? All right, so here's what we do in this lab is we mass them before, we let them set in the solution, we mass them again, and we calculate percent change in mass. Do you guys remember how to do that? Because you're gonna all do that today, because I'm gonna give you results of this potato lab, which is similar to this example I have here, and you have to calculate percent change in mass, and remember it's phi over I times 100, and that is not on the formula sheet, because they're just expecting you to know how to calculate percent. Remember, percent is a part divided by the whole. Okay, and that part happens to be the change. It goes up by 2 grams or it goes down by 3 grams. Divide by what it started with, okay? All right, now, when we graph this, we have our DV over here, and so this must be our IV. So we're gonna put sucrose molarity. Don't forget units. If you go ahead and just put the units here, then it kind of solves all the problems for adding units. You don't have to put units by your number. But this is what drives me nuts, guys, because it takes me forever to grade when you guys hand in graphs and you do this, and I get really irritated with you. If you're going up like by 2, see those numbers? They go up by 2. Then when you're spacing over, space over by an even number. Like if you go up by even numbers, space over by even numbers. It drives me nuts whenever you guys have like 0 and you got to go to 0.2 and you skip 3 boxes. I'm like, well, then when I ask you where 1 is, you can't even show me where 1 is because it's not going to be on a line, okay? So if you have even increments, skip over by even increments. In this case, we can do 4s. That would fill up this whole thing. So if I go over 4, so 1, 2, 3, skip 4 boxes, and I put a 0.2 and put that number right on a line. Because here's the thing, I even like to kind of put a little tick mark there. Here's the reason. If you have to graph this value, 0.2m goes up to 10, and you come over 1 on accident and you go up here and you put 10 and it's not on that 0.2 line, you just missed your point for graphing your data points. Okay. All right. 1, 2, 3. I'm going to put 0.4m. 4.6m, space over 4. Here's my 8. Okay. Now watch how easy this is. Find 0.3. Pretty easy, right? Wouldn't it be right here? What if I say find 0.35? Pretty easy to find, okay? But it's not going to be easy to find where 3.5 is if you only put 3 boxes between 0.2 and 0.4. You have to actually do some math to figure out where your like 0.3 would be. All right, I'm going to do a rough sketch because we don't have a lot of time and I need you guys to practice this. I already know how to do it, okay? So at 0, we had an increase in about 20%. So I'm just going to come up here and I'm going to say my 20% is right here. Just put a dot. At 0.2, we had an increase of about 0.10. So I'm going to just make sure I'm on that line. I'm going to put my here because I am kind of just moving quickly. Okay, notice 0.4, I'm at a -3. So let's call that like right here. But again, it's below the 0 line. See my 0 line? Okay. And then you know what? I can keep on going here, but I technically don't have to because this is the reason why you set up all of this, which takes forever. Okay, I have to set all these up. I have to do all of the percents. I have to graph all the percents because I'm trying to find one flipping number from this chart. So we need to make a big deal out of it. Draw a best fit line, and this right here, right where that line hits 0, make a big deal out of that because you do all of this for this one value, okay? So that's a big deal. Because again, here's what I'm trying to do. I have a zucchini cell, and the question is this: what's the water potential? That's all you're trying to figure out is the water potential, okay? Now, what does this value mean? Draw a line down there, and hopefully you're kind of somewhere around where I was. That would be 0.35m, right? So this value right here, I'm going to put point, hold on, 0.375. 0.375 M. Okay, that would be right here on this axis. What does this mean? It means if I create a solution and I put this much sugar in it, I put this much sugar in the water, 0.375 moles of sugar per liter of water, and I take a cell, okay, and let's say that's a zucchini cell because that's what this question is about. It's about zucchini cells, even though our lab, we use potatoes. Okay, that's a zucchini cell. Okay, and it means that it's not going to have any change in mass. There's going to be a 0% change in the mass. So that means like some water's coming in and some water's going out. It doesn't take on water. It doesn't lose water over 24 hours. And it also means this. What's my concentration of solutes in the zucchini cell for this to happen? It would have to be the same. If I have the same amount of solutes in and out, it's not going to suck water out or in because it's even. So you just figured out how many solutes are in a zucchini cell. 0.375 M. That is this value right here. M. Let me erase that so you can see that better. I think we saw an M earlier, right? Try to make a big deal of it here. So what value did you just find? C. Okay. So where it crosses, that is your C value. Okay. Now that I know the amount of solutes in a zucchini cell, then I can calculate solute potential. Solute potential equals negative ICRT. Notice I soaked them in a sugar solution, and on my formula sheet, it says the ionization constant of sucrose is 1. C, plug it in. So you do all of that work for that one little number, but you have to have that number to calculate solute potential. My other constant is 0.0831. Temperature, I need to add 273 because that's what it tells me to do in the formula. So that's 293 K. Okay. And so I just got, I think it's like negative 13.1, but don't quote me on it, but it's something 13. So I'm just not going to take the time to plug it in. So I just figured out my solute potential, right? Now it says calculate the water potential of a zucchini cell. Sweet. I know water potential is pressure or solute potential plus pressure potential. And I just figured out the solute potential because I used that formula. So water potential equals negative 13.1 bars. I'm not squeezing the cell or anything like that. I'm not changing the pressure of these cells. I'm not squeezing that tissue. So my pressure is 0. So that basically is your water potential, negative 13.1 bars. Okay, 20 minutes. All right, I need you guys to go to Google Classroom, and I need you to open up the water potential lab. And while you're going there, I have a video to show you. Carol made a cameo. And you guys, I'm sure you guys know what a cameo is, right? So do you want to know which star has made the most money in cameos this year in 2020? Does anyone know the answer to that? Which star has made the most money? He's made over $1 million in cameos. Now, if I told you the name, like I can't even remember his name. Like I was like, who? Like I don't even know who this guy is. And he's made the most money. He's like the most famous person for doing cameos. But you all know him if I say, and I'm blanking. Oh my goodness. I quit. My brain's not working anymore. Kevin. It's Kevin on The Office. You guys know Kevin on The Office? Yeah, he's the one that's made the most money. Okay, so I have a cameo to share with you from Carol Baskin for her dear friend's birthday. Hey, Kim.
It's your birthday.
We're gonna party like
It's your birthday.
gonna sip Bacardi like
It's your birthday.
and we don't give a cake, it's not your birthday. Happy birthday, Kim.
Whack-a-mole the kitty.
Oh no, there it goes. I love that the poor cat is like meowing. Like, wait, this cat like has never been the same since that cameo. Have you guys seen her cameo with her husband and she does that? She does it. She's like, we're gonna party like it's your birthday. You gotta watch it. It's really comical. So anyway, we made one for my friend Kim there. All right, you guys have this water potential lab open. And now you guys are going to go through every bit. Imagine I hand you a potato and I said, calculate the water potential. You guys would have to set up all these sugar solutions. You would have to take mass before and after. And then you would have to calculate percent change of mass and graph. Okay. Now I'm just going to give you the values. I've already done this with the potatoes. And here we go. Okay. So what you need to do now is take a picture of this because you need to put in these values on that Google Doc that you just opened. But this is about ready to go away because you're about ready to go into your breakout rooms. So just take your phone real quick or, snap or screenshot what you're seeing now. But you need to write in those values down very, very quickly. I'm going to start to open up those breakout rooms. And you guys are going to get in there and work through this lab in just a second. So give me a second here while you get those values.
We can't see the bottom one.
Right. And you know what? You don't have to see them. All I need is where it crosses 0. And you're going to find that even if you just graph those first 4 data points and calculate just the first changes in mass, you're going to see where it crosses 0. And that's really all that you need. So you don't have to do those extra calculations. It'll save you a little bit of time. But you are right. I didn't have them on there. But you'll see. You won't even need them.
So question.
Sure.
The water potential lab is different from the lab we did yesterday, right?
You know what? Okay, so you know the dialysis tubings that you guys put in the beakers? If I didn't tell you what concentration of solutes was in the dialysis tubing solution that you used, then you could actually figure out like what was the concentration of the solutes in the solution that I gave you. You could figure it out by using that same percent change of mass, graph it, figure out where it crosses C, and then you know what the concentration of that solution was that you put in the dialysis tubing. Okay, so it's very similar lab. That lab is really just to show you, to make sure you guys know how to practice calculating percent change of mass and graphing it. And then that's kind of a warm up. So then if I actually give you some cells or I give you a solution and we don't know what the water potential is or even the concentration of solutes, then you could actually design a lab with very simple tools, water, sugar, and then figure out what the solute potential and water potential is of that solution. Okay. All right.
Does that mean I don't have to turn it in?
If you screw up this next test and you need to reassess, then you're going to want that sucker handed in because I'm not going to give you a retest until it is. So that's totally up to
I took the
you.
last one. So
You what?
the last one kind of screwed me over.
Oh, so you finally took it?
Oh no, I didn't take it at all.
Oh, I didn't think so. Yeah, right now you have a 0 in the grade book. So I advise you to get in there because I'm closing that sucker up at 1 o'clock, which reminds me. So at 1, if you haven't taken that test, it is closing because I'm opening that test for everyone else to go in there and look at the results because you guys have a test on Thursday. And using that first test to kind of study to see what you missed is going to be critical. But you can only open it 1 time and take a look at the questions and see what you missed and get the feedback from it. So make sure you allot that you have 30 minutes to sit down and look at this test because as soon as you close out of it, you'll never be able to open it again. Okay. All right. So let's make sure that you understand you guys are going to basically be working through this. Divide and conquer, or you guys aren't going to get this done. Okay. So some people calculate this one and other people calculate this one. And so work together and you guys will then be able to get more done. All right, so your links are posted. Go ahead and get in your classroom or in your Google breakout room, and then I will see you there in a little bit.